Yeah, I'm going to get started. My name is Jeremy Fink. I'm one of the product development engineers here at Hydro. And today, the topic of this webinar is predictive sizing of the Up-Flo filter on industrial stormwater runoff. And this overview gives a little bit of a background of what we're going to talk about today. Excuse me. I'm going to give a little bit of some context of who Hydra International is, very briefly, for people who might not have worked with us in the past. I'll talk a little bit about the Up-Flo Filter test program that has provided the data for our sizing model. And then I'll go into some detail about how we have modeled the performance of the Up-Flo filter and the algorithm we use to predict performance there. I'll give an example of an inquiry that came in from an industrial dairy, and then some conclusions that you can take away with you. Hydra International has installations all around the world. We operate out of offices in England, outside of Bristol, and on the east and west coast of the United States, Portland, Maine, and then outside of Portland, Oregon, in Hillsborough. And Hydro International does water treatment, stormwater, wastewater, combined sewer overflows. We've been at this for almost 30 years and have installations with all sorts of different applications. In the last 10 years or so, there's been an increase of work on industrial settings, and we're happy to be able to help people in metal manufacturing and scrap yards and things like that manage their stormwater runoff. A big part of what we do at Hydro is research and development, and that's led us to collaborate with universities around the US and around England. So we partner with all these universities. We also partner with several regulatory agencies around the country and around the world. You'll see Auckland, New Zealand in there. North America is well represented, England. So we work with these folks to do regulatory testing, help develop regulatory protocols and things of that nature. We're able to do this largely because of a laboratory facility that we maintain in Portland, Maine. We have another hydraulics lab in England as well, and sort of a burgeoning one in Hillsborough, Oregon. This laboratory allows us to do product development and regulatory testing in our own facility. Hydro's product offering spans the whole gamut of pollutants. Everything from very large gross solids that can be screened out down to materials that are non-settleable or dissolved and need to be filtered out. Hydro has products for each one of these performance classes. The one I'm going to be talking about today is the Up-Flo filter, and it's shown here in this computer rendering undergoing some maintenance, but this is the product that we use for stormwater filtration. And I'll just give a little bit of a sense of how this product works. It's pretty simple. The flow comes in through an inlet pipe, in this case marked A, and enters into a vault or a manhole and fills the sump underneath these blue filter cartridges. And in the Up-Flo filter, just like the name says, the flow comes up through the filtration media and is collected in sort of a manifold at the top of the modules, and then passes out to the outlet pipe marked H. The reason why we use upward filtration is essentially to improve maintenance longevity. You don't need to do maintenance as often. The filter material lasts longer in a fluidized condition, in a fluidized bed. The technology was developed by Dr. Bob Pitt, who recently retired from the University of Alabama. He developed this, and if you were to Google Dr. Pitt, you would see lots and lots of papers that he has published during the development of this technology. Hydro purchased the intellectual property from Dr. Pitt and commercialized it as the Up-Flo filter. He developed it for the EPA as this product called the multi-chamber treatment train. The media that he developed is called CPUZ, and it's not a secret. It's C for carbon, P for peat, Z for zeolite. It's manganese-coated zeolite, and this is a filtration media that's a little bit of a Swiss Army knife. It was designed by Dr. Pitt to do a little bit of everything pretty well. And you can see this has a picture here of kind of a fresh media bag and a spent media bag. This is the media that we deploy on industrial sites. Mostly because we don't know necessarily what we're going to see for pollutants, and we know that this media does a good job in a range of different conditions. So about a year ago, Hydro started a program that is a pollutant removal test program. And when inquiries would come in for the Up-Flo filter for an industrial site, we would say, let's send you a test kit, and that test kit has a bucket and it has some forms to fill out to describe your site situation and some shipping labels. But essentially, this is all a way for you to take a sample from the end of pipe and send it to Hydro, and we would run it through a test. The test was a column test, and we have a column test rig set up, one on the East Coast and one on the West Coast. So depending on where the site is, we might change where you ship it to. But this column test was designed to be analogous to a full-sized Up-Flo filter. It has the same depth of media in the column. It is loaded at the same loading rate as an Up-Flo filter. It has the same flow distribution. And so the idea is we can use this column test to make some estimates about how the actual full-sized unit would perform. And the next step is Hydro will take samples from the influent of that column, a subsample from the effluent of the column, send it off to a third-party laboratory for analysis, and put together a report. So this report would go back to the potential client and would give some indicator about whether the Up-Flo filter and the CPUZ media was appropriate for that site runoff or not. And so this is, we've done lots of these sorts of reports and column tests for potential clients. So for example, in this, what you see here in this chart, each one of these bars represents one of our test results. We feel very strongly that we are making our sizing estimates based on real runoff. It's very easy for a media supplier or a filter supplier to test their equipment with lab standard. And lab standard is something you would buy from a laboratory supply house. It's deionized water that you have added only the ions of the dissolved metal that you're interested in. And because you've added them to such a pure solution in such a pure form, they're very easy to remove. So those would give you some high removal rates if you were to test with lab standard. Or sometimes you'll hear people say that they're using real runoff spiked with lab standard. It's sort of the same thing. You're diluting your real runoff with lab standard. We feel it's important to use actual runoff. Best case, the actual runoff from the site that's being evaluated. Why is this so important? the fact is that I don't have a chemistry background, and so I've got a few points up here that people have told me this is the theory behind how the media works. My background is mechanical engineering, but I'll just explain quickly what the theory is. The media has certain adsorption sites, and people on this call might understand this actually better than I do, but adsorption sites that pick up the pollutants through ion exchange. And so if you have real runoff, now you have lots of different ions in your runoff competing for the media sites, the adsorption sites on the media, competing with the metals of interest. And so that becomes complicated. Also, copper has some ways of binding to organic compounds that can make it difficult to remove. And then there's the issue of irreducible concentrations, which I'll get into a little bit here in a couple of slides. So over the last year, we've collected 31 discrete samples from 6 unique locations. All 6 of those locations have been in California, primarily because that's where the regulatory drivers are strongest. We have 4 different industrial applications. There's scrap yards, metal manufacturers, food manufacturers, and then we have 1 municipal client that is discharging to a sensitive ecological area, so they're concerned about their metals. We have samples from fall, winter, and spring. Anytime it's raining in California, we have samples North and South California. 30% of the tests are from field installations, and you can see in this picture here, there's a manhole installation of the Up-Flo Filter in this black plastic manhole. In that case, the entire system was delivered to site and runoff was pumped through it. So that's kind of a full-scale pilot unit, and then 70% of the samples were sent in a bucket to our column test rigs in the lab. It's worth noting that this is a different kind of test than maybe what you've heard about in the past in conferences and things. Very often, media tests and media reports are built on the back of a particular site that's maybe having trouble meeting their performance benchmarks, their runoff benchmarks, and they'll engage a consultant who throws the book at it and says, all right, I know about 10 different medias. We're going to put all 10 different medias on site. We're going to try them all, and I'm going to publish a paper that describes which medias worked well, which medias didn't work well, and that becomes the topic of the study. This is sort of the inverse of that, right? We have only CPUZ media, that is the media that is used in the Up-Flo filter, but a variety of different site chemistries, a variety of different test cases, the way that the media is being treated on site or in the laboratory. So it's sort of the inverse of a typical study. So the next question that you get asked always is, what % removal did you get? And the answer is, it's complicated. Percent removal, each one of these bars here represents what % removal we saw on a certain test. And as you can see, we had some tests that gave us better than 95% removal, and we had some tests that gave us almost 0 removal. So what does that mean? I could say to somebody, well, our average removal is 60%, but that's not especially useful for someone who's trying to size or select a technology for their site. And I could even say, you know, that I could give some kind of statistical understanding of there's a max and a min and a quartile and this sort of thing. But still, it's not a great way for anybody to predict performance. Percent removal implies that you have a linear relationship, a clear correlation between your influent concentration and your effluent concentration, and that 100 micrograms per liter will reduce to 20, and so 1,000 milligrams will reduce to 200, and 10 will reduce to 2 every time, and it's just not going to happen that way. There's irreducible concentrations. When you get down to some very low numbers, you are going to see lower percent removals. And if you have very high numbers, it's very easy to show good removals. In fact, what you'll often see is people spike their test media, their test solution with higher concentrations so that they can show a better percent removal. So, okay, percent removal maybe is a tough way to predict performance. Is there a better one? I'm just going to just drive this point home a little bit more. Here's each one of these green dots here represents one of our 31 test cases. If percent removal was a good indicator of what we were seeing for performance, you would have a line that all of these points would be along that line with a linear relationship between your influent concentration and your effluent concentration. Clearly, this is not true. More to the point, the average variance, so if you were to use, let's say, the average percent removal, if I selected, say, 60%, and I said, okay, I'm going to use 60% as my average, I'm going to vary off of my prediction is going to vary from my actual test result by almost 44 micrograms per liter. This makes it really not very useful in California, where the numerical action limit is 33 micrograms per liter. So even if the model predicts that I'm going to be under my numerical action limit, the range of accuracy of my prediction says I could bounce right out of that range and over the limit again. There are other ways to predict models, predict performance, but none of them are much better. You might think, well, maybe loading rate is a good way to predict performance. You put more water to the filter, it's not going to perform as well. Yes, to a certain degree, but still the variance is high enough that it's not a particularly useful performance. And you might use some of your theory, and maybe you've studied this enough to know, well, total metals usually come in a particulate fraction and a dissolved fraction. And a higher particulate fraction is going to be easier to remove. So maybe a high TSS concentration coming into the system would give you better performance. That doesn't necessarily show good correlation either. So what do? What we did is used a multivariable model, which is a statistical tool that allows you to take several linear correlations and roll them all together into one large expression. And we use a statistical package called R. You can get to it from this link shown here. It's an open source package. It's pretty easy to use. There are lots and lots and lots of online courses to show you how to use it. I recommend this one at Coursera. It's an excellent one. What this statistical model does is it, to use a big word, produces a phenomenological model, easy for me to say. And this is a model that is not really based on theory, but it's informed by theory. It's an empirical relationship that really just describes how the system behaves. And we have to use a little bit of our, and I'll go into some detail about this, we have to use a little bit of our understanding of the theory to set up the model, but the actual results that come out are just about system behavior and the data coming out of the system. So this is the fit we get from the multivariable model, and this is something that is actually useful to us. We have an average variance of about 4 micrograms per liter. This is copper, and this is kind of a model where we have test results on the x-axis and the model result on the y-axis, and if they tie up, they fall along that line. So that's 11% of the California NAL. That's pretty useful. The zinc has a little more scatter. Our average variance is 22.5 micrograms per liter, but the California numerical action limit for zinc is 260 micrograms per liter, so we're still about 10%. So that's a useful model for us. Now, when you're putting together statistical models, there is some best practices to follow. And one of them is that, statistics, you can sort of make them say whatever you like if you cherry pick your data going in. So that the cardinal rule is thou shalt not cherry pick. These are all of the 31 influent concentrations that were used to make up our model. And you can see we're relying, in our model, we're relying on 4 variables: copper influent, zinc influent, TSS influent, and the loading rate of the system. And on this chart here, or these 4 charts, excuse me, the left axis, the y-axis, that's a logarithmic scale. So there's quite a bit of variance in the copper and zinc concentrations. Copper is just less than 2 orders of magnitude. Zinc is a little more. There's one very, very high entry there. TSS is maybe a little over 1 order of magnitude variance in our samples. Loading rate we have some control over, so that really doesn't vary quite so much. Maybe 1. Really, it's just very close. So every one of these data points was used in the model with no sort of selecting. I won't spend a lot of time here. This is the only equation in the presentation, but I thought it was worth including for anybody who really wanted to understand what's going on under the hood of a multivariable regression model. What the software does is takes the data and does a linear fit, just like you would if you were doing an Excel linear fit, a trend line in Excel or something like that. Only it does it not only for one variable, but it does it for every variable you ask it to do, and products, every possible product of those variables. And it makes an estimated coefficient for each one of those situations. And so you end up with 15 estimated coefficients and an intercept. And it puts this into one long expression. And that's what you get out of your statistical software. And it produces a chart like this. Here are the 16 coefficients, and it sort of lists them in order of what it says the magnitude of the effect is. So this is where you have to start being a little careful with correlation models. And the call goes out, correlation does not imply causation, and that's to say just because 2 variables are correlated does not necessarily mean that they are linked causally in any way. And in this case, you can see the number 1 magnitude effect is assigned to some interaction between loading rate, TSS influent concentration, and copper influent concentration. Well, what does that mean practically? The thing is that it's really hard to say. And you could look at this and try to back theory out of it, but that's not really good practice. You don't want to look at correlation and say, aha, so that means that this is going on. This model is strictly a model of the behavior of the system. However, it's built, we chose these variables because our theory is that copper influent, zinc influent, TSS influent, and loading rate would all have effects on our final resulting concentration, our effluent concentration. I don't know if you've ever seen this. There's a website there in the corner there. It starts with T. I can't quite read it here, but he's got all of these data sets that correlate, but clearly are not causally related. So, you know, this is cheese consumption and civil engineering doctorates. Now, the point he's making here is these are two variables that were not chosen carefully, like the ones that we are using. This is two random variables, and so you can't really assign any link between them. You know, you would not actually look at this and imagine that PhDs drive the cheese market, or you could make some sort of prediction about cheese demand by looking at the enrollment in engineering programs. So, but we've got a lot of, knowing all of that, we have a lot of confidence in the model that we've developed because the 4 independent variables that we've chosen, copper, zinc, TSS, and loading rate, theoretically should make a difference on the performance of the filter. Not only that, we were able to do what we did with the model without making any concessions for test rig, geography. For example, there's no flag in the model that says, oh, this is a scrapyard, so you have to adjust the model this way, or this is a this was done in a full-scale unit, or this was done in a column unit. The only variables involved are the ones that theoretically should make a difference. So I'm going to go through sort of an example of what happens when we get a inquiry and we use this model to make some predictions about performance. This is an example from an industrial dairy. They came to us with some numbers. They said, well, our TSS is around 150 milligrams per liter. We have a range of zinc concentrations that we're trying to reduce that go from 600 to 1200 micrograms per liter. We don't have much issue with copper. Okay, I'm not sure what that means, but let's go on. And they want to know, what's the estimated performance? This is not their facility, but I'm guessing maybe it's similar with galvanized roofing and the zinc is coming off there. It's possible. So the first thing we do is look at these concentrations that are going to be the potential influence and say, is this something that is in the family of our model? Have we seen this sort of thing before and cooked it into this algorithm? This chart maybe looks a little confusing, but it's a very sort of visual thing. The green dots here are our 31 points that make up our model, and the orange sort of glowing points are what was predicted to be the influent of the dairy. This is what they're going to be trying to reduce. And if those glowing points are basically within the cloud of points that we've modeled as part of our algorithm, then we can have some confidence and say, yeah, we've seen this sort of thing before. It should react basically like all the other points we have run through this, this test program. We can make some predictions. So the one thing that I was maybe a little bit cautious about when I was looking at this was the chart on the upper right-hand corner, the zinc concentration versus the copper concentration. They said they didn't have much problem with zinc. And so what does that mean? Well, typically we look at zinc concentrations and copper concentrations that are pretty close to each other. And so if they had a very, very low copper concentration and a zinc concentration up around 1,000 micrograms per liter, and then we'd be outside of what we've seen in the past. And I might still make some predictions, but with the caveat that this is slightly new ground, and I would want to get some more information. So the numbers that I gave in this example made an assumption that the copper was greater than 10 micrograms per liter. And so out of that performance model, we get these points. And this is, I don't know if you've seen a chart like this before. These are influent and effluent pairs. So they gave us a high zinc and a low zinc influent concentration. Shown here, the high zinc concentration is the orange and yellow lines, and the low zinc concentration are the green and gray lines. And then I modeled it with a high loading rate of 15 gallons a minute per square foot and a low loading rate of 10 gallons a minute per square foot. Well, regardless of whether we had a high zinc or a low zinc concentration at our influent, we got close to that dotted red line is the California NAL for zinc. So we got close to it, but you know, that might be a little too close for comfort. My suggestion was that we size this unit for 10 gallons a minute per square foot, more likely to get under that limit. And that's kind of how Hydra would use the model to make predictions and estimation about the performance of the filter. So just a few conclusions here, and then I'm going to wrap up. Estimates of filter performance on an industrial site should really be based on real runoff, not some kind of laboratory standard or a spiked sample. Preferably, if you can get it, get a sample with your own runoff, because every site has unique chemistry, and you really need to know what technology is going to do with your water. Percent removal is maybe a good, very, very, very rough shorthand of how a filter is going to perform, but a better estimate of performance is something that takes into account more than one variable. We use 4 variables, and on average, our copper correlation is within 4 micrograms per liter. If statistical packages are not part of your toolkit yet, they've I think the online learning has happened sort of on the back of the big data movement that's underway right now. There's lots of good online learning, and highly recommend it as a tool for anybody who has to deal with large amounts of information, and could really help your runoff program, your stormwater program. And lastly, this is a work in progress for us, and we want to keep partnering with people. If you have a stormwater problem, an industrial stormwater problem, and are looking for a partner, we want to hear about it. We want your data. Even if the Up-Flo filter is not a good match for your site, please request one of our free sample kits, and we'll run it through our column test and let you know what we find. So that's the last slide. That's the end of the presentation. Thanks very much for attending. If you have any questions, feel free to email them directly to me at my email address shown on the screen here. There is an exit poll that is associated with this webinar. We'd appreciate it if you took the time to answer that. There are PDHs that are associated with this presentation. They are scheduled to go out next week. I think Monday, March 27th, they should be arriving via email. And I think that's all. Thanks very much for attending, everybody, and have a great rest of your day. Bye-bye.